Hi everyone. In this lecture, we'll discuss about the impulse response of parallel RLC circuits. We are going to feed a current impulse to a parallel RLC circuit and then observe the voltage developed across the RLC tank. So for the current impulse, I've assumed, since we said the units of the current impulse has to be charged, I've assumed a charge of Qi entering the tank, entering the RLC circuit. So to avoid any confusions with Q of a parallel RLC circuit, there is already a Q of a parallel RLC circuit. To avoid confusions, I just used a different term for the charge. Now first we'll try to solve mathematically what is the voltage across it, and then we'll try to derive intuitions towards the end of this lecture. So to solve this problem, I'll just use Laplace transforms. I'll multiply the input Laplace transform, the current Laplace transform, with the impedance of the parallel RLC tank. We already derived this expression in the last class. The impedance of this, for low frequencies it will behave like an inductor, high frequencies it will behave like a capacitor, and at the resonant frequency it will behave like a purely resistive element where both the current and voltage will be in phase. So we already derived that expression. So here I'll just quote the final result, which is this. Now I'll use this result omega naught equals 1 by root LC and Q for this, which is RP by omega naught L or RP into omega naught C. Okay, so again we discussed the definitions of Q for a parallel RLC circuit. It is the ratio of admittances, okay, 1 by omega naught L by 1 by RP, so you get this. So since they are in parallel, we take the ratio of admittances. You want to find how reactive the element is. Q tells you how reactive the element is. In a series RLC circuit, we took the ratio of omega naught L by this to be the Q. But in a parallel RLC circuit, the one with the higher admittance matters. Okay, so that's why we took the ratio of admittances. The ratio of admittance for an inductor is omega naught L by 1 by RP, and you get this expression. Okay, so that's the definition of Q, and I'll use this Q and omega naught in this expression, and I'll get this modified expression for the transfer function, the impedance function. Again, this expression should make sense. Now at omega equal to omega naught, this term and this term will cancel out, and you will be left with the ratio of this and this, which is 1, and the impedance is simply equal to RP at the resonant frequency. Okay, so again I'll take the omega naught in the denominator to the numerator. We can further reduce this expression in this way. So we will get RP into S omega naught by Q. Now if you substitute Q as omega naught RP into C, then I will be left with Qi. So this term will actually, this product of Q RP into omega naught by Q will reduce to Qi by C. So that should make sense. It's an impulse of charge you are injecting into a parallel RLC tank. The impulse of charge at high, whenever the input is applied, when you apply the impulse, at the instant the impulse is applied, it's like a sudden change. So therefore the network sudden change amounts to a high frequency input. So the parallel RLC circuit will behave like a pure capacitor. So if an impulse of charge is fed to a capacitor, a step voltage will develop across this, and the magnitude of the step, the value of the step, is simply Qi by C. And I'm going to call Qi by C as V naught. Okay, so now we have an expression for the tank voltage in terms of V naught, which is Qi by C, the initial voltage, and a Laplace transform, and again we have the impedance transfer function. Now we need to find the inverse Laplace transform for this function. So we have to try to reduce this in a form which we are already aware of. So something like, for example, the Laplace transform of cos omega naught t into u of t is S by S square plus omega naught square, but this is different. There is also an S term here. So how do we deal with that? So to solve this, first I'll look at the characteristic equation, which is the denominator polynomial of the transfer function. So you have omega naught by Q plus omega naught square equal to, I'll just equate it and try find the poles. Now once I know the poles, we know that the transfer function can be expressed as a sum of a linear combination of partial fractions. You can express it as partial fractions. Then we can easily compute the inverse Laplace transforms. So I'm just trying to find the poles using this. So I'll directly write the expression for the poles. It will be omega naught by 2Q plus minus omega naught j omega naught into root of 1 minus 1 by 4q square. Again, the poles here are complex conjugate poles, and this is valid if the poles are complex conjugate if q is greater than or equal to half. And for most ideal, even radio frequency circuits, this condition will normally be valid, q greater than or equal to half. So the poles are nothing but S1, 2. These are the two poles of the system. They are complex conjugate poles. Now if you see, both these poles are on the left of plane because the real part of the poles is negative. So I am going to call this omega naught into root of 1 minus 1 by 4q square as omega d. So this would be minus omega naught by 2q plus minus j omega d. So you have the poles on the j omega axis, and I'll draw the real part, which is minus omega naught by 2q. So the pole is actually, if you draw a line from the origin, this will be the line for the line to the pole, and if I compute the angle theta that this line makes, the vector, or the line that makes from origin to the pole, the line that is drawn from origin to the pole, and if you compute the angle that line makes with the real axis, and I take tan of theta of that will turn out to be simply equal to omega d by omega naught into 2q. Okay. Now for large values of q, if your q is very large, then omega d will approximately be equal to omega naught. You can see that from this expression. If q is very large, I can ignore 1 by 4q square, okay, compared to 1. So in that case, your tan of theta will actually be equal to 2q, the q of the parallel RLC circuit. Okay, and it should also make sense. Now let's say q is infinity. If q is infinity, what would happen is that the omega by 2q, this point, the real part of it will become 0. No, the pole would move, the real part of the pole would move to 0. This term will become 0, and the complex conjugate, the poles will then become purely imaginary. This will become omega d will be equal to omega naught, okay, if q is infinity. Okay, then the poles will be purely on the j omega axis. Okay, so now that we know the poles, okay, we know both the poles, we will try to find, so this is plus minus omega naught by 2q, sorry, this is minus omega naught by 2q plus minus j omega d. Okay, now what I will do is I will take this term to this side and I will write it in this way. So the characteristic equation can also be written in this way. Okay, so initially the characteristic equation was s square plus omega naught q by qs plus omega naught square equals 0. Now we just modified it to this form. Now I'll substitute this in the expression, so which is v naught s by s plus omega naught by 2q the whole square plus omega d square. Now I'll use one of the Laplace transform properties. If x of t, the signal has a Laplace transform of x of s. Now you multiply x of t by e power minus 18 to u of t, then the Laplace transform will get shifted. This is called the frequency shifting property. So you will actually have x of the Laplace transform of the signal is going to be x of s plus a. Now if you look at this expression and try to compare it with the cos signal, so cos of, I'll call this term as sigma as omega naught by 2q as sigma. So if I have cos omega dt into u of t, the Laplace transform is going to be s by s square plus omega d square. Now if I multiply it by e power minus sigma t into cos of omega dt into u of t, then the Laplace transform of that is going to be s plus sigma by s plus sigma whole square plus omega d square. And we've gotten a very similar expression for the transfer function here as well. So now what I'll do is I'll just add plus sigma and then I'll subtract sigma, so you will actually get the expression in this term. Okay, now sigma is nothing but omega naught by 2q. Okay, And this term here, this looks like a sine wave. So if I have sine of omega dt into u of t and multiplied with e power minus sigma t, the Laplace transform is going to be omega d by s plus sigma the whole square plus omega d square. So I'll just multiply and divide by omega d here. I'll get now, after this I'll take inverse Laplace transform. So this is going to be v naught e power minus sigma t into cos of omega dt minus sigma by omega d into cos of omega dt. Okay, sorry, this is sine of omega dt. Now sigma by omega d, now here I'll make an approximation. So this term sigma by omega d will normally be a very small number, okay, or I can also, yeah, I'll make an approximation here. So sigma we know is omega naught by 2q, and omega d is omega naught into root of 1 minus 1 by 4q square. Now for large values of q, this can be approximated to 1 by 2q. So the expression is actually v naught, there is a u of t multiplied here. So I'll come back to the expression to this can be written as sigma of e power minus sigma t into omega dt. I'll approximate it to omega naught for large values of q minus 1 by 2q into sine omega naught t, okay, into u of t. Again this term again can be further reduced, so you'll actually have e power minus sigma t into cos of omega naught t plus phi. I can write it as a single cos signal with an amplitude a. Now the amplitude a will simply be root of 1 plus 1 by 4q square, okay, and theta is going to be tan inverse of 1 by 2q, okay, or phi is going to be 1 by 2q. You can now for large values of q, in fact I can ignore the second term and simply write it as v naught e power minus sigma t into cos of omega naught t into u of t. Now this expression, if I try to plot this, so first I'll draw the exponentially decaying signal e power minus sigma t, and then the cosine signal is going to be okay, eventually it's going to go down to 0 because as t tends to infinity, this function will tend to 0, okay. It's like an amplitude sinusoid whose amplitude is varying with time, and it's actually exponentially decaying with time. Now for a lossless LC circuit, if you remember, we fed an impulse to a lossless LC circuit, and we observed that if I fed an impulse of say charge Qi, the initial voltage developed was Qa by C, and the solution was actually cos of omega naught t. And that should also make sense because the charge is instantly stored across the capacitor, and the voltage of Qi by C is developed across it. Then the charge energy is transferred back and forth between the inductor and capacitor. It's never lost. But now in a parallel RLC circuit, every cycle some amount of energy is going to be lost in the resistor. Because it's going to be lost, the amplitude of the sine wave is going to reduce. I mean the energy in the system is going to reduce, which in turn I can say, for example, the energy in peak energy is half C V square, V naught square at t equal to 0 on the capacitor. Now that is going to reduce, so that can be seen as a reduction in the amplitude. Okay, in the presence of a resistor, some amount of energy is going to be lost as dissipated as heat in the resistor. So that accounts for reduction in the amplitude, and eventually all the energy will be depleted by the resistor itself or dissipated by the resistor itself, and eventually the voltage will come down to 0. Okay. So that's about the impulse response. Now one of the useful applications of impulse response is by visually inspecting and finding the Q of a parallel RLC circuit. So sometimes the circuit may not be accessible, so you may have to just feed an impulse and look at the output, and by looking at the output we can actually predict the Q of the parallel RLC circuit. So how do we do that is, I'll try to write e power sigma t into cos omega naught t into V naught. We'll try to compare this term. E power minus sigma t tells you, let's say there was no sinusoid, which was a pure RC circuit, it would have just decayed down. If let's say there was just R and C, and if I fed an impulse to this system, impulse of current, I know that the initial voltage would have been Qi by C, but it would have instantly decayed down to, after some time it would have decayed down to 0. Now to find time constant, what I would do is, I'll just start with the initial value and then see what is the time it takes for it to say reach 5% of its initial value. Okay, so what is the time it takes? So for example, we know within 3 time constants this value is going to be around 95 point, so it's very close to 4 to 5%. It's going to come to 4 to 5% of its initial value within 3 time constants. If you can watch one of the previous lectures where we discuss about first order RC circuits, you can actually see that when we, after 3 time constants, the exponential decay is going to be very fast, so it's going to decay down to just 5% of its initial value, for 4 to 5% of its initial value. Okay, now using that, or even lower, it's going to come to that, very close to 4 to 5%. So from that, I'll compute 3 time constants, value of 3 time constants, by just looking at the time for which the value becomes 5% or 4 to 5% of its initial value, and from that I can calculate the time constant of this RC circuit. Okay, even if let's say I don't have the access to the RC circuit, I just have the impulse response of the RC circuit, then from that impulse response I can guess the time constant, okay, by monitoring the value of the time constant and seeing at what time that it reaches 4 to 5%. Then I'll approximately equal it to the time as 3 time constants and find the time constant from that. In a similar way, we can actually find the time constant of or the value of Q. Here we'll later see that it's a similar mechanism here as well. Time constant Q also determines the time constant of decay. If you look at this, it's getting decayed. The waveform is actually getting decayed. A higher value of Q would means the losses are lower, therefore the decay will be slower. If Q is infinity, there will be no decay at all. Because there is no loss of energy, so therefore it will be an everlasting sine wave. Okay. So now what we will do is, we will try to monitor, because it's a sinusoidal, there is also a sine wave present in this signal. Unlike a first order system, there is also a sine wave here. It's a second order system. We will try to count in number of cycles. Okay, let t be the time period, which is given by 2 pi by omega naught. So what I am going to do is try to compute t sigma into sigma. I'll write it as omega naught by 2q into nt. I am going to compute n cycles before which the amplitude reduces to, at the nth cycle I am going to look at the amplitude of the sine wave. Okay, this is the, you start from here, this will be the end of first cycle, this will be the second cycle and third cycle and so on. Okay, I'll look at the amplitude of the sine wave after say n cycles. Then I'll find out when this becomes equal to e power minus 3, because for a first order system, e power minus t by 2, when t equals 3 tau, you get e power minus 3. So I just want to compare when this is close to e power minus 3. So what I'll do here is, I'll substitute omega naught into t, here is 2 pi. So this reduces to pi into n by q, e power minus. Now to compare the result better, what I'm going to do is, I'm going to compare it with, instead of 3, I'll compare it with e power minus pi. Pi is very close to 3, pi is 3.14. So I'll try to compare it with 3, pi. So this equation tells you that if I advance by q cycles, okay, where q equals n, if q equals n, this term will be equal to e power minus pi. So what does it mean is, if I advance by q cycles, where q is the RLC tanks q, then the amplitude of the waveform will reduce to e power minus pi, or it will come back to nearly 4% of its initial value. Okay, so from that I can you just have to calculate, that is the time constant for which it reduces, or if I just monitor the number of cycles by which the amplitude becomes 4% of its initial value, that number of cycles will be equal to the Q of the circuit. Okay, you can also find the time constant of decay, but here we are interested in Q. If you know Q, for a parallel, for a resonant circuit, Q is more important than time constant. Okay, it captures the loss in the circuit. So we talk in terms of Q. So after Q cycles, the value becomes 4% of its initial value. So by visually inspecting the graph, you can actually say that, okay, by just visually looking at the graph, you can roughly find what is the Q. Okay, so you just have to count the number of cycles, 1, 2, and say by third cycle it comes to nearly 4%, then Q is equal to 3 for this system. Okay, now 4% will be very close to 0. So when you are visually inspecting a impulse response, you can simply count the number of visible cycles. Of course, if you zoom in this region, you will find more cycles. Let's say in this region you will find, but visually when you are seeing the whole waveform together, if the initial amplitude is large enough, then you can easily just count the number of visible cycles. That will also approximately be equal to Q. But to be exact, you have to start from the initial value and see when it reaches nearly 4% of its, the peak value becomes 4% of its initial value. At that point, approximately that number of cycles will be equal to Q. Okay, so that's how, given an impulse response, you can measure the Q of the parallel RLC circuit. And if you remember, this is time domain. From time domain, we are estimating the Q of the parallel RLC circuit. Now, in case I give you the frequency response, you can also estimate the Q of a resonant or a second order parallel RLC circuit from its frequency response. Okay. Now we discussed in the last class a parameter called bandwidth. So we have omega naught by 2q and plus omega naught, and omega naught minus omega naught by 2q, as you know, the 3 dB frequency points, where the value reduces to 1 by root 2 of its peak value. Now the bandwidth is simply omega 2 minus omega 1. From the graph you can compute the bandwidth, and you'll also know omega naught. Then if you take the ratio of omega naught by bandwidth, you get the value of Q. Okay, so that's what we discussed in one of the previous lectures. So given a frequency response, you can find the value of Q. At the same time, if you are given the time domain response, you can also find the value of Q from that time domain response. Okay, from the time domain response you can also compute the resonant frequency and all that. But Q is one important thing. By visually it's very useful for circuit designers. By just looking at the waveform, you can just, to a first cut, you can actually very easily predict the value of Q from the time domain response. Okay, so that's it about Q and impulse response of parallel RLC circuits. So now I'll try to give a small intuitive explanation comparing the bandpass RLC response, okay, to a low pass response. So if you look at the bandpass RLC response, we discussed RLC impedance, the frequency response of the RLC circuit, the impedance of that, it was actually something like this. You had at the center, and we also defined two terms called the 3 dB frequency, which is omega naught plus omega naught by 2q and omega naught minus omega naught by 2q. Okay, both of them extend to this extends to infinity after that, and so on. Now I'll first consider a function for frequency response which actually is centered around origin, okay, but with the same bandwidth. It's from omega naught by 2q and minus omega naught by 2q. This is for both positive and negative frequencies. So I'll first consider this transfer function, and then if I frequency translate it by omega naught, then I'm going to get this frequency response. Okay, so how do you frequency translate it? You just have to convolve it with impulses in frequency domain. So first I take a function like this, frequency response like this, which is low pass frequency response, and then convolve it with an impulse centered at omega equal to omega naught. Then you get the frequency response of a parallel RLC circuit. Now if you look at this is simply a first order low pass filter. You just have a pole at the 3 dB bandwidth is at omega naught by q. So I can simply say the transfer function for that, the impulse response of a first order system is, it's a first order system, so you have a pole at omega naught by 2q. So you can very easily say the transfer function will be of this form, 1 by s plus omega naught by q, omega naught by 2q. So inverse Laplace transform is e power at, which is e power sigma t into u of t, where sigma here is omega naught by 2q. Okay. Now if I convolve it in frequency domain, that is equivalent to multiplication in time domain. And if I have impulses in frequency domain, it's nothing but a cosine signal. So if I take this and multiply it with e power cos omega naught t into u of t, then I get the bandpass response. So the time domain response can also be derived from the frequency response itself directly by looking at it as a frequency translated low pass filter. So this is the impulse response of a low pass filter, and if I frequency translate it, it becomes a band pass filter. Okay. So and band pass response, I'm using the word filter, but it's, I think now by now you understand what it is. So yeah, so this is the band pass response of a parallel RLC circuit in the time domain. Okay. So I just gave a different intuition for it. It's pretty much, I mean, if you've already understood how to do it from time domain, it's pretty simple, but this is also another way of approaching the same problem. Okay, so I'll stop at this point. In the next lecture, we'll start discussing about the frequency, the impulse, the step response of a parallel RLC circuit, and then probably we'll also discuss about series RLC circuits. Okay, so that's it. I'll just stop at this point.